This video is part of my exploration of traditional Chinese mathematics. We will demonstrate how Yang-Hui's triangle, also known as Pascal's triangle in English, can easily provide us with a formula for the sum of piece powers of 1 to n for any positive integer p. Let's start with reviewing the property of Yang-Hui's triangle. As we can see from the picture, Yang-Hui's triangle has rows that start and end with 1. Furthermore, at any row, a number in between the two ones is the sum of the two above it in diagonal. Yang-Hui's triangle is closely related to the expansion of any power of the binomial. Indeed, for any integer n, the coefficient of the expansion of the binomial a plus b to the power of n appear in the n plus first row of the triangle. So, Yang-Hui's triangle can be seen as a table containing all the coefficients for every binomial expansion. Now, let's take the cubic expansion of a plus b as an example to find the general formula for the binomial coefficients. For instance, how do we calculate the coefficient of ab squared in the final line? During the expansion, we take either a or b from each parenthesis and multiply them together to form a product that contains 3 factors. This coefficient is equivalent to the number of ways we can fill 3 blank spaces with 2 b's at once, regardless of the order. This number is exactly the combination number 3 choose 2. More generally, the coefficient of any product appearing in the expansion of a plus b to the power of n is n choose m. These coefficients compose the n plus first row of Yang-Hui's triangle. How are the rows of Yang-Hui's triangle related to each other? To answer this question, observe that a plus b to the power of n plus 1 can be written as a plus b to the power of n multiplied by a plus b. Expanding both sides of the equation and comparing the coefficients with the same powers, we can deduce the n plus second row of Yang-Hui's triangle. Now, let us uncover the hidden summation formula in Yang-Hui's triangle. Let us consider the 3. 3 is the sum of numbers on its left and right shoulders, as well as the sum of the numbers above it in diagonal. Due to the property of Yang-Hui's triangle, 6 is the sum of numbers above it in diagonal. Similarly, the sum from 1 to 4 is 10, the sum from 1 to 5 is 15. Now, 15 corresponds to 6 choose 2, which is 5 times 6 over 2. Therefore, we can deduce that the sum from 1 to n is n plus 1 choose 2, which is equal to n times n plus 1 over 2. In its right adjacent diagonal, each number is the product of 2 consecutive natural numbers over 2. Their sum equals n plus 1 choose 3, and is located at the lower right of the end of the diagonal. In a similar way, we can easily find the sum of all numbers from 1 to the end of any line parallel to the left hypotenuse of Yang-Hui's triangle. These formulas appear in the Yuan Dynasty mathematician Zhu Shijie's famous work, Precious Mirror of the 4 Elements, from the 14th century. Let's see how these formulas can help us in finding the sum of higher integer powers of the first n natural numbers. We can rewrite the square of any natural number n as 2 times n minus 1 over 2 plus n. Observe now that if we sum them on the left-hand side of the equation, we obtain the sum of the squares of the first n natural numbers. On the right-hand side, 2 old friends appear. The sum of the numbers on the purple and the sine diagonals of the Yang-Hui's triangle. Therefore, the sum of the squares from 1 to n equals 2 times n plus 1 choose 3 plus n plus 1 choose 2. After simplifying, we derive the final formula for the sum of the squares from 1 to n. Observe now that we could derive the same result by writing n squared as the linear sum of n choose 1 and n choose 2. You may think that if we can write n cubed as the linear sum of combination numbers, then the formula for the sum of the cubes from 1 to n would become apparent. So, how do we find the unknown coefficients alpha 1, alpha 2, and alpha 3? Don't be scared by the complexity of the combination numbers. Patiently unrolling the formulas, regrouping the terms with the same powers, and solving the equations in the alphas will get us to the desired solution. Modern Chinese mathematician Hua Luogeng suggested another approach based on the method of successive differences to derive the coefficients of the combination numbers. To understand it, consider the cube of n as an example. In the first line, write the numbers from 0 to 3 to the third power. Then, take the differences between two adjacent numbers on every row and keep doing so until there's a single number left. Observe that the numbers appearing on the left side of the reversed triangle are exactly the coefficients of the combination numbers found previously. Now, you may want to take a few seconds to apply this method to find a closed formula for the sum of fourth power or any higher natural power of the numbers from 1 to n. Interestingly enough, the formula for the sum of the cubes of the numbers from 1 to n and the successive difference method were already known by Zhu and appeared in his book, Precious Mirror of the Four Elements. An example of the application of the above formulas is to find the area below the curve y equals x squared between 0 and 1, as presented while introducing the definite integral in calculus. Indeed, dividing the interval from 0 to 1 into n equal parts, each of which is 1 over n wide, and taking as the rectangle's height the value of the function at the right-hand point of each interval. Then, the total area of these n rectangles, Rn, encloses the formula for the sum of squares from 1 to n. After some manipulations, we get the simplified expression for Rn. If we increase the number of rectangles that approximate the area under the curve, 1 over n gets closer to 0, and Rn approaches 1/3. In this opening example of integration, using the formula for the sum of squares from 1 to n and the idea of limit, we realize that by summing the areas of increasingly small rectangles, we can find the area under the parabola. Now, let's come outdoors for some inspiration and build a tetrahedral. The bottom layer is a triangle with n balls on each side. As we ascend, each layer has one last ball, leaving one on the top. Song Dynasty mathematician Yang Hui then asked, how many balls are used to form this tetrahedral? In the comment section below, interested friends can discuss which diagonal of Yang Hui's triangle is used for this summation. Yuan Dynasty mathematician Zhu Shijie proposed finding the total number of balls in a sequence of tetrahedra. Would you like to play and build your own pattern of stacks or even an architecture? And then enjoy figuring out the math behind it.